Hello and welcome back. Let's finish off these proofs of functions being within orders of other functions with this exercise here, where we are going to show that log base 2 of 4 to the n plus 1 is on the order of little o of n squared. So as a reminder, what does this actually mean? Well, our little o of g of n, so f, whoa, that was odd. Never had that happen before. Okay. Uh, f of n is going to be within little o of g of n if and only if for all m greater than 0, there exists an n naught greater than 0 for all n greater than n naught, where f of n needs to be less than or equal to m times g of n, which again is effectively us saying that f of n needs to be less than g of n because that m is arbitrary. We don't get to pick that m. So it doesn't mean that we may not need to use the m to solve our problem, but we are sort of, we want to make sure we understand that basically the point is that the m does not affect the inequality in any way. So let's just start by writing out our inequality from our original problem space with this in mind. So m greater than 0 is arbitrary. What is our n naught going to be? To get log base 2, 4 to the n plus 1 being less than or equal to m times n squared. Okay, so again, we need to figure out what that n naught needs to be. So in order for our n to have a value, we get to pick our n naught. And we hate that that fractional space. So what happens if we let our n naught be greater than 1, as we've been doing over and over again? Well, if our n naught is going to for sure be greater than 1, we get to use our round up trick, because we can see that if this is going to be here, that will definitely be less than this right here, because n is going to be greater than 1. So it'll definitely be greater than that. And this is going to be really important, because then we can rewrite this in another way that makes our life a lot easier. Where we're going to say log base 2 of 2 times 4 to the n. Now, having that is really important here, because this log of 2 times 4 to the n is basically the same thing as saying log base 2 of 2 plus log base 2 of 4 to the n, which when that is then calculated, leaves us with that 1 over there, log base 2 of 4 to the n. Now this log base 2 of 4 to the n, we can do log base 2 of 4. Whoops. Log base 2 of 4 is going to be 2, and we know that. If that n wasn't there, we would know that, which means we get to bring down that n, and we're going to end up with 1 plus 2, and this 2 here, to the n. Sorry, not to the n, times n, because we can bring that n down and do log base 2. Because effectively, a reminder that 4 to the n is basically like saying 2 times 2 to the n. So we could have expanded that one more time out and ended up with log base 2 of 2 plus log base 2 of 2 to the n, which would then allow us to bring down that n factor. So I'm just doing it in one fewer steps. But we can actually follow that math all the way through as long as our n is definitely going to be greater than 0. And since we get to define our n naught, we can make sure that our n naught forces that n to be above 0. That's fine. This tells us that we probably want to make sure that our n naught is going to end up being hopefully at least 1, right? We know we're going to need it to be at least 1 for this to work. So once we've gotten that far, we'll be able to finish sort of determining what our n naught needs to be by also considering the other side of this, right? We have to figure out the other side over here. So now we have log base 2, 4 to the n plus 1 is less than or equal to 2 to the n plus 1, which is less than or equal to m times 2 to the n squared. So how are we going to do this? Well, we've already proven this for if n is greater than 1. Now let's look at the other side over here. Well, if n is greater than 1, if that is true, we can round up again. We can say 2n plus 1 is probably less than or equal to 2, well, I guess less than 2n plus n, because n is greater than 1, and we have a 1 right here. So we get to use our roundup trick, where this is then 3n. So 2n plus 1. Let's write the whole thing out again. I think it's always so helpful to see it all in one line. 4 to the n plus 1 is less than, I guess is less than 2 to the n plus 1, which we're now saying is going to be less than 3n, which is going to be less than or equal to this right here. So now we can work with this. We can divide both sides by n, and we end up with 3 less than m n. And if we divide both sides by m, we'll find that 3 over m less than n. So we can see we need our n to be greater than 3 to the m. And we also know that we need our n to be greater than 1. And so with these two pieces of information together, we can ensure that we set an n naught that considers both of these. So let's let our n naught equal 3 to the over m plus 1. In doing so, we'll ensure that regardless of how small our m is, if m is very small and this is very large, we will definitely be over n greater than 1. And if instead m is very large, which will make this whole term very small, we use this to ensure that we're still going to push ourselves up and over that n greater than 1 term. So this could be written in a way that has the max function, but it's just not necessary, because if we just say that we let n naught equal 3 over m plus 1, we're going to observe that that means that n is going to be strictly greater than 3 over m plus 1, which is n being strictly greater than 3 over m and n being strictly greater than 1, which are the two things that we needed it to be based on the above rough work. So given these two pieces of information, we can observe that while n is greater than 1, it's true to say that this is going to be less than this. I'm not going to rewrite all of it. And then when n is greater than 3 over m, we're able to also say that starting from 3 over m being starting from this, if we multiply an n into both sides, we'd have n squared like this, right? And then we multiply an m into both sides, and we'll end up with this. And that, and since our n is greater than 1, we know that that's going to be greater than that. And we've gone ahead and proved that side as well. Again, I know that that's not particularly formal proof, but all this graph work is there, and you can use this value and your class notes to actually walk through how to structure this as a formal class time proof. And there you have it. That is the last one in this exercise set. And next week lectures, we're going to look at some new properties of these asymptotic values from asymptotic notations. And we will be finishing it off with some kind of more abstract puzzle proofs of asymptotic properties rather than looking at specific function values. So I'm very much looking forward to that. Thanks, everybody. I hope you have a great weekend, and I'll see you in the next video.